So vectors are quantities with both direction and magnitude. Let's say you have the movement of a ball and it travels through the air like this. Well, vectors are graphically represented by arrows, so look like this. The length is decided by the magnitude, and the direction, so where they point, is decided by the direction, which is usually an angle or a compass bearing, like northeast. Now, when we write vectors, the symbol is going to be an arrow. Now, you can add vectors in multiple ways. First way is graphically. Graphically adding vectors, however, has a problem. It's not sufficiently accurate. For example, let's say you have two vectors here and you want to add them graphically. Well, you could use the parallelogram method, which looks something like this, and you'll get your result. These methods are cool, but I'm not going to teach them. They're good for visualizing and checking your math, but the most powerful, precise way is adding by components. Adding vectors by components basically means you add the x part and the y part, because every vector has its x part, its x component, and his y component. Well, let's see this concept in action. So let's take a vector, and we're going to call this vector v. Vector v is broken down into two components. We have the y part, so we'll call this v with a little y, and the x part, which we'll call vx. You can imagine this as a right angle triangle, which means that to find this vector's magnitude and direction, we can use trigonometry. Now let's do some quick equation deriving. To find the y component, we can use sine, because remember, sine is opposite, so opposite this angle, and divided by the hypotenuse. So opposite over hypotenuse is vy over v. Oh, sorry, I forgot to write the angle. Now, if you multiply both sides by v, then you get vy is equal to v sine. This is the formula for the y component. If you go and do the same thing with the x component and use cosine, because remember, adjacent over hypotenuse. If you go and do it with cosine, you get vx equals v cosine. So these are the formulas for the magnitude of the x and y components of vector v. Now, how about the magnitude of v itself? You can use Pythagoras because it's a right angle triangle. That means v2 is equal to vx2 plus vy2. In this video, to solve problems, I'm going to be writing it as v equals root vx2 plus vy2, which just skips a step and it makes it a little easier. And I want these videos to be efficient for you while also not skipping too many steps. Now, how about finding the direction, which is the angle? The direction can be found with tangent. So let me make some space up here. The direction is tangent equals vy over vx. And the reason why this is because if you remember from trigonometry, tangent is also equal to sine over cosine. And sine is the y coordinate, cosine is the x coordinate. Now again, I'm going to simplify this formula a little bit. Instead of writing all this, I'm going to be writing it as the angle is equal to tan minus 1. So the inverse of tan times vy over vx. Same thing. I highly recommend you write these formulas down somewhere in your book. We're going to be using them today. Here we have two vectors. So this one we'll call v1 and this one we'll call v2. When you add them up, the resultant vector looks like this. Because you just have to connect the tail of the first one to the tip of the last one. And we'll label the resultant vector as vr. Now this resultant vector, what if you wanted to find the components of it? Now here's an important thing. The sum of all x components equals the x component of the resultant. So the x component for this red vector, which we'll call vrx, is the sum of all x components. So that would be the x components of vector 1 plus the x components of vector 2. Same with y. So all the y components equals the y component of the resultant vector. So let's use that. This is the x component and the y component of vector 1. This is the x component and the y component of vector 2. This is the y and x components of vector resultant. That means this vector here plus this vector here equals the length of this vector here. Same with the y. This one here plus this one here equals the length of this one here. And then once you find those values, you can go ahead and use Pythagoras to find the magnitude of the resultant vector itself. That's the basic concept behind adding by components. It's very precise and you're going to be using it a lot in 2D kinematics. And here's a rule to remember. Do not add x to y. Do not add them together. Add y to y and add x to x. Here's our first example problem for today. So you have a hiker and he goes on a journey. He travels 5 kilometers east. And then he decides to travel 12 kilometers at 30 degrees north of east. Let's break this down. So first let's resolve each vector into its components. This value we'll call v1 and this value we'll call v2. v1 has these two components. The x is 5 kilometers east and it doesn't say he goes up or anything, so the y is just 0. Now v2 is a little bit more tricky. If you remember the formulas for finding the x and y components with trigonometry, that's what we're going to have to use. So it gives us 12 kilometers as the magnitude for this vector. The x component, if you remember, is equal to 12 times cosine 30. 12 is the magnitude of the resultant vector, which is where we got 12 from. And then cosine 30 was cosine of the angle. Same with y. Y is equal to 12 sine 30. Now we just have to add up all the x's and all the y's. Now let's start with the x values. So x1 plus x2, when you put it into a calculator, you get 15.39 kilometers. Now y1 plus y2, these two guys, is equal to 6 kilometers. We can go ahead and use Pythagoras, but I want to show you what this looks like on a graph, because in a test, you might be asked to graph out vectors as well. Now 5 kilometers east, that can be like this. And then 12 kilometers, 30 degrees north of east. What does that mean? North of east means you start going north and then you tilt 30 degrees to the east. So it looks something like that. And the 30 degrees would be here. The resultant vector, it goes from the tail of the first vector to the tip of the last vector. So the tail of the first vector to the tip of the last vector. Looks like that. And remember, we're adding these y components up and these x components to find this and this, 6 and 15. If you went ahead and used Pythagoras, you would find that the magnitude of this vector here is roughly 16.52 kilometers. Now how about the direction? This mystery angle here. Now if you remember, you can use the inverse of tangent to find the direction. So tan -1 of y over x. So y is 6 divided by x, 15.39. Put this into a calculator, you get roughly 21.3 degrees north of east. There's our two values for this vector, the direction and the magnitude. There we go. Let's go through a bit of a harder example. This one has 3 parts, so it's got 3 vectors going on, not just 2 like the previous one. Imagine a fighter jet on a recon mission. And first, he moves 800 kilometers north. And then let's say he gets spotted and he has to escape. So then he goes 600 kilometers, 35 degrees east of north. Then lastly, he has to return back to base. He travels 900 kilometers at 50 degrees south of east. This is his 3 movement paths. Now before we go through this together, I want you to try and solve this yourself. It's going to take a bit of thinking, but give it a go. Now let's go through this together. So break down the vectors into components. Let's do that first. Now the first vector, we're going to call him D1 for displacement 1. This one we'll call D2 and this one will be D3. Now D1, the X component is 0 and the Y component is 800 because what we're going to use is just north going up as Y and X can be east and west. That's our frame of reference. Next, D2 has an X component of 600 cosine 35 and a Y component of 600 sine 35. Finally, D3. D3 has an X component of 900 cosine 50 and the Y component is 900 sine 50. There's all our components and we just have to add it all together. But we can't forget this. This Y here is going to be negative because he's traveling south. Now we're ready. We just have to add all of these X's and Y's together. So all the X's, if you put it into a calculator, 1070.1 kilometers. So that's his X vector. How about Y? Well, when you add all the Y together, you get 454.4 kilometers. If you went and graphed this out, which is optional, but I like to do it to visualize whatever's going on, it will look something like this. So he travels 800 north, then he travels 600 kilometers east of north. So that would mean east and then you tilt up to north. So 600 kilometers. And then south of east, 900 kilometers, which will look like that. And the resultant one we're looking for is this. And we'll give him a name dr for resultant. So here's the X component of dr. And here's the Y component of dr. With this information now, we can go and use Pythagoras. So dr is equal to root drx plus root dry, all of it squared. Go and plug in your values and you get roughly 1162.2 kilometers. The direction, remember we just used tangent. So the Y over X, which is 450 over 1000. And this is roughly equal to 23.1 degrees northeast. So there we go, direction and magnitude. Now we've just gone through some very heavy addition stuff. So we're going to move on to subtraction and multiplication now. Subtraction and multiplication are very, very simple compared to addition. Now let me make something clear. No vector is ever negative in the sense of its magnitude. It's always positive in terms of magnitude. Rather, negative shows the direction. So let's say you have a vector v. The negative version of this vector, it would have the same length, so the same magnitude, but it would be going the other way. So same length, opposite direction. Multiplication is even more simple. Vectors can be multiplied by what's called a scalar, and we're going to call it c. So c times v is a vector with the same direction as magnitude v. The only thing that changes is the magnitude. So let's take vector v1 again. Let's say it looks like that. Vector v2, which is 1.5 times v1, would look 1.5 times longer, but in the same direction. What if you multiply it by a negative number? Multiplying it by a negative number changes the magnitude and then flips the direction. So let's take a third vector. And this vector is equal to negative 2 times vector 1. This one would look like vector 1 here, but flipped and 2 times longer. For every topic I cover, I like to create a free cheat sheet. And I use them myself as well. So if you want your own with all the formulas you'll ever need in one place, then go sign up in the description.